there is this 4x4 matrix, and you're supposed to oversee, it's supposed to calculate a minimal operator for each of the vector. And this part B was lacking, so that's why I'm explaining. And use the factored form to find the basis of the Jordan canonical form. So here, you found all of these. T times the t minus 10 squared, and that's the minimal operator, right? So here, t times the t minus 10I squared, this is the minimal operator. You all got that correctly. But the next part is not well understood. In part B, you're supposed to get canonical form. So now I was in earlier class, and in very disorganized form, it was explaining that once you have this form, you can get an eigenvectors for free. And from here, all you did is just row reduction. You didn't calculate any determinant, right? Usually you do determinant to calculate eigenvectors, right? You got for this E1, we have this nice minimal operator, E2, E3, E4. You got this nice minimal operator. By just playing with the minimal operator, you get eigenvectors for free. So this is minimal operator. You stick E1 into that. Did I do that? Well, I reorganized it in here. So I did that. E1, go through t minus 10i, it becomes this vector, -8, -2, 2, and -4. Then this vector go through t and becomes 0, right? That's the eigenvalue 0. Right? It's 0 times that. Kernel is eigenvalue 0. So I get this eigenvector for free. I got one eigenvector of eigenvalue 0. So don't go to next vector. You just swap it. Go through t first. Then you go through t first. You get this vector, 2, -2, 2, and -4. Okay? Then that vector is replaced by that. And then you're left with this operator, t minus 10i. Right? What is this one doing? It becomes a 0. Anything, the kernel of this one is the eigenvalue 10, right? Eigenvector 10. So I get one eigenvector of eigenvalue 10 for free. So I got two eigenvectors. So you go to the next one. You do the same thing. Let's do the T2. This time the minimum operator is this. You go through T2, T with E2, then I got this vector. 4, 6, -6, and 2. Because it's a minimal operator, this one, if you go through t minus 10 one time, it's not going to be 0. But 2 times it's going to be 0. This is the Jordan chain, right? This is the Jordan chain. So start with the V2. You get this TE2 that I call the V2. And if you go through 2 times, and you can see you arrive at here, the V1, that one is an eigenvector because you go through that t minus 10i becoming 0. We have one eigenvector of eigenvalue 10. I have another vector of eigenvalue 10. As long as these two things are linearly independent, we have another eigenvector of eigenvalue 10, correct? So I looked at these two vectors, and here's another eigenvalue 10. Compared it, that they're not linearly independent. They are linearly independent. Therefore, this is new one. But instead, not only an eigenvector, I have a Jordan chain. V2 and V1 becoming this. So I have one eigenvector and another eigenvector and Jordan chain, right? Jordan chain gives you two independent vector. So I have only 4 vectors now. But that must be it. So I'm checking eigenvalue 0, eigenvalue 10, eigenvalue 10 with Jordan chain. And I row reduce it. They're all linearly independent. They are the basis. These two are eigenvalues, eigenvectors, and this thing form a Jordan chain. Therefore correspond to Jordan block. There's a good chance that if you have a minimal operator, just rearranging it, you have Jordan canonical form for free. And that's actually how the proof is actually manipulating the existence of not actually playing with this one. They just say, there exists this thing and that thing, and this is a good example that you actually feel this everything. So nobody did this 1B correctly, and I explained it in a very unorganized way last time, so I'm explaining here. Is that all right? Does that make sense? You see this interesting part of this information? Yeah, you get this eigenvalues and Jordan chain for free without doing any determinant calculation. All right, that was that.